further. Now there is an example, right? What I would want you to do is that do this example yourselves. Do this example yourself. So read it. Calculate the radius of the largest interstitial void in the FCC gamma iron lattice, right? So the diagram that you just passed in the previous slide is the diagram, because you see, if it is FCC gamma iron, then it means that, right? So the atomic radius of the iron atom is 0.129 millimeter in the FCC lattice, and the largest interstitial voids occur at half 0, 0, 0, half 0, 0, 0, half, etc. type positions. Right? So go back to the previous diagram in one way, that if it is steel, then it is iron and carbon. But they just want to find out, because we were saying that the radius or the diameter of carbon is slightly larger than the interstitial void. So it will form some distortion. So now we want to confirm that is this true? So forget about the carbon that is coming in. Just think of iron. Just think of iron, that we have only iron. And the radius is 0.129 nanometer, and it is an FCC, right? So don't go further in the slides, as we always ask you. Try to draw an FCC cell, right? First, right? Just a cube with FCC, a cube with FCC. So that is there. That is the gamma iron. Gamma iron is FCC, and each atom is 0.129 nanometer in diameter, and there is some size A. Of course, you know the FCC rule, right? Root 3A, root 2A, whatever. So you can find the A size if you want in terms of the atomic radius. That is one thing. We need it, we don't need it, you will see. So this is one thing, right? You draw a cube and draw an FCC cube. So FCC, it is an FCC iron. So on every face there is a central face atom, right? And each iron atom is 0.129 nanometer, and you can find. Now draw the point half 0, 0, half 0, 0, or the point 0, half 0. You will see that these points are special points. So on the cube, draw these points, okay? Also, you can take only one face. Draw a diagram of any one face, not the whole cube, any one face. There are 4 corner atoms and 1 central face atom, right? And they are all equal size. Remember, they are all iron. So you have 2 diagrams. One diagram of the whole cube and one diagram only of one face. And then, right, try to find out this size or this gap by simple geometry. By simple geometry. A circle is there, so the size of a circle, the radius, the diameter is there. If you can make a triangle, and it is a right triangle, then the Pythagoras theorem will be there. So if you know one side and the other side, you can find the third side. And one side is A, one side is R, and so on, right? So don't look into the next slide. Try to do this yourself, right? And I leave you with that please don't go forward in the lecture slides. Next time when we come, we will start with the solution very quickly, because you would have already tried this solution, right? So just draw an FCC full cell, assuming that each atom is iron. Then draw only one face of this, showing the 4 corner atom and the central face atom. And you know that you can find the value of A if the radius is given, which is given in the problem as an FCC. And then you can try to make some triangle in which some sides are known, some sides are unknown, and you can find the interstitial gap. Okay, so here we will stop. We have done only 2 methods of solid solution: the substitutional method, for which the Hume-Rothery rules can be applied, the 4 rules, and the interstitial method, where the solute is much smaller in radius or diameter compared to the solvent, so it can go and fit inside the interstitial locations. So substitutional solid solution and interstitial solid solution, and these are the two methods by which all of the alloys are made, whether the alloys are metal to metal or metal to non-metal. We will inshallah come next time, and please keep on looking at your email, and please keep on checking your Moodle for the lecture notes and for these videos and any other announcements. Thanks a lot. See you next time. Masalama. So you see, this is your whole thing. You have uh, right. You have this full cube. It is an FCC, so all the four corners, 8 corners, there are atoms, and on every face there is an atom. But we were talking of the points. So if you take, say, right, any one of the planes where, so we are taking the point 0, half 0. So you see, in X you do not move, in Y you move half, and in Z you do not move. So on this line, the center of this line is 0, half 0, 0, half 0. So the point 0, half 0 is on that back face, the 100 plane, right, on the back face. So only that face you draw separately here, right? Only that shaded where the point 0, half 0 is there, 0, half 0. Any other point could also be there. If you see, if you say 1, half 0, so you will be on this point. Then you take the front face again, right? You start from here, it is 1, half 0, so you will be on this point. So you could take the front face, but we are taking the back face. If you are taking the back face, this is the back face. These are 4 corner atoms, and there is a central atom on this face, and all atoms are equal in size, right? Now one side is A, this side or that side, anything. And if you see, from here to here there is R, right, the radius of the larger atom. Similarly, from here to here is capital R, the radius of the large atom. And the, if in this place, in this is the 0, half 0 place, 0, half 0. So here draw an atom which touches and fits. It touches this one, it touches this one, it touches that one, it exactly fits roughly, right? And assume that the radius of this small one is small r. So the distance from here to here is 2 small r, 2 small r, right? So this is what you have to draw. That first you draw the whole cube. On that, take the point 0, half 0. See which face this point 0, half 0 is on. For that face, just draw the face. That face means that there will be 4 corner atoms and 1 central atom on that face, each of the radius capital R. And then inside, on this location, draw a small solute atom with radius small r, right? So now you see, you take this radius, from this center you draw a line to this center, from that draw a line to this center. These are the 3 touching atoms, isn't it? This is capital R radius, this is capital R radius, this is a small r radius. So you draw this rectangle, this triangle, this triangle. Now this triangle we are drawing separately here so that you can easily see it. This line is R here, capital R, and capital R here. So this is 2 capital R. This line of the triangle is 2 capital R. This side is exactly A, and this is halfway there, halfway, right? This is in the center. So this side is half A. This side is half A. Similarly, this side is also half A, right? But this side, half A, is R plus a small r, isn't it? It is capital R plus a small r. So now this is your triangle. This is your triangle. So half A square plus half A square is equal to 2R square, right? This will be your equation. So this is it, and then you can find, right? Then you can find, and so on. So otherwise, this half A is equal to R plus a small r, right? R plus a small r is also equal to half A. So with that, you start. Now there is no issue. You have 2R plus 2R is equal to A, or you have 2R square is equal to half A square plus half A squared, which you found from the other side, and so on, right? So you solve this equation, you will simplify it, you will get 2 capital R is equal to 1 upon root 2a, or leave a here, this root 2 will go there, so a is equal to 2 root 2r, right? A is equal to 2 root 2r. Now this we know anyhow. I mean, if we had not done this, we will still know that for FCC, a is equal to 2 root 2r or whatever, right? So there, and from the equations 2 capital R plus 2 small r is equal to 2 root 2r, you solve it, simplify it, ultimately r will come to be 0.053. Of course, the unit you should not forget, all distances are in nanometers. The capital R, the small r, the a, they are all in nanometers. So this small r is 0.053 nanometer. So this means that the void at the location 0, half 0 is 0.053 nanometer. So any solute atom which is 0.053 nanometer or smaller than this will directly fit in that gap, and any solute atom which is slightly more, for example 0.06, it will fit inside there, but it will push the atoms outward slightly, so the lattice constant A of the solvent material will slightly change. So you see, this way you can easily find that if we want to make interstitial solid solutions where the solute atom is small enough to fit inside the interstitial gap, then what size of atoms can go in there? So if a metallurgist wants to make an alloy, right, for example, if you see iron, you will see the radius of iron, right, capital R. You will see the radius of uh, right, the radius of carbon, and you will see whether it is exactly equal to 0.053 or it is slightly larger than that. And that way then you can right, decide whether you can form a good alloy or not. Okay. So slide, we have finished one portion of the chapter. You see, the chapter is solid solutions, one part, and crystalline imperfections, the other part. So solid solutions are only two types. They are substitutional solid solution and interstitial solid solution, and we have covered both of them now. So we now start the second part of the chapter, which is crystalline imperfections. Imperfections or defects that are there in solid materials at the crystal level. When I say brief coverage, I want you to think that, you see, in this portion of crystalline imperfections, we will just give you the concepts and explain what these defects are, but we will not do in so much detail that we do the numerical problems. So we can do numerical problems in solid solutions like we have just done, but in crystalline imperfections, we will not do that. Okay. So that is good news or bad news, whatever you feel. We will, right? So crystalline imperfections. Now, why are we talking of imperfections or defects? Because they are the things that affect the mechanical properties or the chemical properties or the electrical properties, right? You see, you have made an alloy. You have made copper nickel or lead tin or iron carbon. You have made the alloy, and these alloys or these materials are crystalline in nature. So if there are certain defects, then those defects will affect the mechanical properties. Now there is a very nice systematic way in which we are going to cover these defects. 0 dimension, 1 dimension, 2 dimension, 3 dimension. You see, that is how we will go. So it is very simple to remember. 0 dimension is just a point, 1 dimension is a line, 2 dimension is a plane, and 3 dimension is the solid volume. So we will think of defects in a crystal at a point level, at a line level, at a plane level, and at the volume level. So 0 dimension defect, 1 dimension defect, 2 dimension defect, 3 dimension defect, right? So this is how we will go, and rather than reading what we have here, we will go into them and we will see what defects are there. So of course we start